Solution concentrations. So you add table salt to water, and it looks like it disappears, right? It's like, oh, magic, disappeared. But of course we know that it didn't disappear. If you taste the water, you can tell that something has happened, right? So the table salt dissolves in the water, forms a homogeneous mixture. Now, if we took that salt water and boiled all the water away, the salt would be left. It didn't go anywhere. It just mixed with the water. Well, a homogeneous mixture like that of salt and water is called a solution. Here's another example of where we use words a little differently in chemistry. In everyday life, a solution is, a fix for your problem, right? In chemistry, it's a homogeneous mixture. Solutions have two basic parts, the solvent and the solute. And all these words start with SOL, which, helps us know that they go together, but it can also be a little confusing. There's always one solvent. It is generally present in greater amount. So if you look at the amounts of the different things in this solution, the one that there's more of is generally the solvent. Another feature of the solvent is that it keeps its state. Now when you put salt in water, the water is still a liquid. The salt becomes part of this mixture now, which is a liquid. And so in a way, the salt has changed its state, right? It's gone from being a solid to getting mixed up with the water. Now it's acting like a liquid. But the water stayed the same. So that can help you decide which is which too. The solute is generally present in lesser amount. The solute may or may not change state, and you can have more than one solute. Because what if you took that glass of salty water and you threw some sugar into it? Now you've got two solutes. The solvent is still water. There's always one solvent, and then everything else is dissolved into that. Solutions are mixtures, and so the composition can vary. You can have a little bit of salt in the water. You could have a lot of salt in the water. And that's what distinguishes solutions from pure substances. Pure substances have constant compositions. Saltwater samples are solutions. If you take samples from different areas, different oceans or different lakes, they're going to have different amounts of salt because it's a mixture. So when we're describing a solution, we have to tell how much of each component is present. Pure substances can be described with a single name. We can say, oh, that's carbon dioxide, because all the particles are the same and there's no variability. We can't say, oh, that's salt water. Well, is it really, really salty, or is it just a little bit salty? We have to describe how much. We have qualitative terms, and these are dilute and concentrated. These are relative terms. They don't have numbers associated with them. A dilute solution is going to have a small amount. Well, define small, not large, right? A concentrated solution is going to have large amounts of solute. Okay, and what may constitute a concentrated solution for one combination of solute and solvent may be very different from what constitutes a concentrated solution for another. But if we compare these two solutions, we would say this one's concentrated and that one's dilute. This one has fewer solute molecules and this one has more. Relative terms. We also have quantitative methods, and the one we use the most in chemistry is called molarity. This is very similar to the word morality. If you just swap the R and the L, you get morality. It's molarity. And it has to do, molar should make you think of not teeth, but moles. Okay? It has to do with the number of moles of solute. And as we just learned in chemical equations, it's really important to know how many moles, because that's what the equation tells us the ratio's about. So chemists care a lot about moles, and so the concentration unit we use the most has to do with moles. So molarity is abbreviated with a capital M, and it's the amount of solute in moles divided by the volume of the entire solution in liters. And so it has the units of moles per liter. So this moles per liter. Now we need to be a little careful with our m's. Is that a capital M or a lowercase m? Lowercase m? It's a capital M. Oh, I can't even spell molecule right now. My point is, it's hard. Well, it should be pointy, yes. But I don't always make my M's pointy when they're capitals. That's my son's name, Michael. Doing this is tedious, right? We often don't do that. So when it's typed, you can clearly see that it's a capital M. When it's handwritten, it can be kind of iffy. So what a lot of chemists do, if we have a 2.0 molar solution, so that we're very clear that that's a capital M and not a lowercase m, which would mean meters, is we will underline the capital M. So you'll see me do that, and I just want to tell you what that is. So amount of solute in moles divided by volume in liters. When we make a solution with a specific concentration, there are some specific steps that we would do. Here's an example of making a 1 molar. When you read this, you'd read this 1 molar NaCl solution. So this is a volumetric flask. Can you even see that? It does have a neck here. It's kind of hard to see. It's got a neck. I should probably adjust the projector or something. You're going to figure out the mass of 1 mole of sodium chloride, because if you have a 1 liter bottle or 1 liter flask, you need 1 mole per 1 liter to make a 1 molar solution. So you figure out the mass using its molar mass, and you weigh out that amount of sodium chloride, and you add it carefully to the flask so that all of it gets in here. Then you add water part way up, and you mix it around. The volumetric flask has a long, skinny neck for a reason, because there's this mark, you can see it over here. There's a mark on the neck, and it is calibrated so that when the bottom of the meniscus of the solution is at the mark, it is 1 liter. And on the flask, it will generally tell you plus or minus, 0.001 liters or something like that. It'll give you the uncertainty. But if you fill it all the way up here, it's going to be very difficult to mix. And the reason we have the narrow neck is because then a small change in volume will be a large change in the height of that surface. And so we can get it more accurate. But it's not good for mixing. So you put water in here and just part way, where you still have some airspace here, and you swirl it around until all of the salt dissolves. And then you top it off and add water right up to the mark. At that point then you have to put a stopper on it and invert it to finish mixing it. And we always stick our thumb, imagine I'm holding one of those, stick our thumb over the top of the stopper so that when you tip it over, you really don't want the stopper to fall out, right? It shouldn't fall off, but who knows, right? If it's really important, it will. Murphy's Law, it follows me, so it's going to be here. You put your thumb over it, you invert it several times to mix it.